Hi students, in this video we are going to study the second part of common microscope, that is when the final image is obtained at infinity. Okay. So let us see what is the ray diagram for this. This is the principal. This is the principal axis. As I told you, objective of smaller aperture and smaller focal length, and we have the eyepiece of comparatively I am saying larger focal length and large aperture, and here the object is placed beyond the focus of the objective. And remember, in the case of simple microscope, to obtain the image at infinity, where must be the object placed? Object should be placed at the focus of the lens. The same way, here the ray of light, after refracting through the lens, meets at a point, and the image, final image of the objective is obtained at the focus of the eyepiece. The distance between the lens is adjusted in such a way that the image of the objective, that is A is the object, A dash B dash is the objective, is formed at the focus of the eyepiece, and the rays from this image, which act as a virtual object for the eyepiece, passes through the lens, and since object is placed at the focus, the image will be formed at infinity. Now this angle is this angle is beta. So let us see once more the diagram to obtain the image at infinity. For that, the object is placed beyond the focus of the objective, and the ray of light, after passing through the objective, meets at a point, and the image, we get a real inverted image A dash B dash at the focus of the eyepiece. From there, this image acts as a virtual object for the eyepiece, and the rays passes through the lens, and they won't meet at a point, they diverge, and the final image is obtained at infinity. Now u0 is the object distance of the objective, v0 is the image distance of the objective, ue, which is equal to fe, is the object distance of the eyepiece, and remember, all the distance should be taken from the optic center of the lens. Now let us see what is the equation for magnification. Okay, the equation for magnification, the detailed derivation is not required here. Okay, so here AB is the object, A dash B dash is the image, and this angle is beta, and the magnification produced by the eyepiece is given by ME is equal to B by FE, and the magnification produced by the objective is M0 is equal to minus L divided by F0. Therefore, the magnification of a compound microscope when the image is at infinity is M0 into ME, which is equal to a minus L by F0 into B by Fe. So this is the magnification equation for a compound microscope when the image is at infinity. Now if you compare this equation with the magnification produced by a compound microscope when the object or image is at the least distance, we get the equation as minus L by F0 into 1 plus B by Fe, which means that magnification is more when the image is obtained at the least distance but strained to our eye. Next, we are going to study about telescope. We are all familiar with the optical device telescope, isn't it? It is an optical device used to see distant objects clearly. Now, telescope is of two types. First one is refracting telescope, and the second one is reflecting telescope. From the name you can understand which type of spherical surface we are using here. Reflecting telescope. Refracting, which means we will be using what? We will be using lens. In the case of refracting telescope, we will be using convex lens, and this refracting telescope is again of two types. First one is Astronomical Telescope, which we use to view space, celestial objects like planets, stars, etc. And second one is terrestrial telescope. The one which we use to view objects, distant object on the surface of the earth. And reflecting telescope, the one which reflects means it is a mirror. So we will be using basically convex or concave mirror for reflecting telescope, and it is also of two types. The first one is Newtonian telescope, which was discovered by Sir Isaac Newton, and also Cassegrain telescope. So telescope means what? It is an optical instrument which is used to see distant objects very clearly, and it is of two types. Which are the two types? Refracting telescope and reflecting telescope. And refracting telescope is again of two types, and refracting telescopes are one which uses the lens, and it is of two types. That is astronomical telescope, the one which we use to view space or celestial objects, and next one is the terrestrial telescope, the one which we use to see the distant object on the surface of earth. And reflecting telescope are the telescopes which make use of mirrors, convex mirror and concave mirror, and it is of two types, Newtonian telescope and Cassegrain telescope. Now in this video we are going to study about Cassegrain telescope, and there is no need to study the derivation for magnification, but you have to study the ray diagram, and you also must study how the telescope works. Now Cassegrain telescope mainly consists of a parabolic Cassegrain telescope mainly consists of a parabolic concave mirror is parabolic, which means it is more curved, concave mirror, and also a convex mirror. Now what is the use of parabolic mirror? It is because mirrors usually have a defect known as spherical aberration. Spherical aberration means, in one of the videos I have told you, we use two types of rays to study for the study of ray diagrams in optics. One is the marginal ray, and next is the paraxial ray. Marginal rays means the rays which enters or which touches the mirror at the end points. And next one is the paraxial rays. The paraxial rays means the one which are closer to the principal axis. Now if the mirror is having a larger aperture, what happens is that the marginal rays will meet at a point after reflection, and the paraxial rays will meet at a separate point, which means after reflection all the rays, instead of meeting at the focus, they will be meeting at different points. So, you won't be getting a clear image, you will be getting a blurred image. So, in order to cut off the marginal rays, what we do is we make the the mirror more parabolic, more curved, so that lesser number of marginal rays will enter the mirror. So, for a quasi-grain telescope, we are using what mirror? We are using a parabolic concave mirror. Now, let us see the diagram of a quasi-grain mirror. So, we have a parabolic concave mirror. This is the principal axis of the mirror, okay, and there is a very small opening at the center of the concave mirror. Okay. Now, this mirror is known by the name primary mirror. Okay. Now, we all know when a ray of light which comes from infinity or which comes from distant, a very distant point object, what happens? After reflection, it meets at the focus, isn't it? Now, here also same thing happens. A ray of light from a very distant object, it incident on the mirror, and then what happens? It undergoes reflection and it must meet at the focus. But before meeting at the focus itself, we keep a convex mirror in front of it, in front of the focus of the concave mirror. What we keep? We keep a convex mirror. So, what happens is that the ray of light after incident on the concave surface gets reflected and it touches the convex mirror. It comes and hit the convex mirror, from where it gets again reflected and meets at a point which is somewhere here, and here we can obtain the image of the distant object, and using an eyepiece you can view the object. I hope this is clear to you. The rays from the distant object comes an incident on the concave mirror, it gets reflected, and before meeting at the focus, what happens? There is a convex mirror kept in front of it. So, rays get incident on the convex mirror, and from there again it gets reflected and meets at a point where the final images of the object, distant object, is formed, and this final image is viewed using a eyepiece. Now, the magnification equation for magnification of a quasi-grain mirror, when image is at near point or at these distance of distant vision is m is equal to f0 by fe into 1 plus fe by, for microscope it was d by fe, here it is fe by d, and when the image is obtained at infinity, we get the equation for magnification as m is equal to f0 by f. So, in the case of quasi-grain or reflecting mirrors, you need to study the diagram, the working, and also the final equation. No need of detailed derivation of the equation for magnification. Thank you.